Well, hi everybody. Welcome again to another exciting session of our Mathematical Methods CAS course. And today we're going to have a look at something which is a little bit a little bit crazy, because this stuff is family of functions, and not only is it families of functions, which implies generic kind of functions which all belong to the same kind of family tree, and we're going to look at applications of differentiation within that context. Now, what am I talking about? I'm talking about, fasten your seatbelts guys, that's what I'm talking about, because we've got we've got CAS, which is computer algebra systems, we've got pronumerals everywhere, and we've got literal equations, which usually sends people into a tailspin. However, never mind, we are going to conquer, and today's theme is yes you can, and you definitely can. It's all a question of whether you believe you can, because I'm no smarter than you, and I can do it, so you can too. That's right, you're a star. And we'll go far. Now, this first one, look at all the A's and the B's in that equation. A and B are positive constants, with B is bigger than A. Now, alright, let's just go with it, and we're going to conquer it. What have we got to do to it? Number A, find the derivative of f of x with respect to x. Well, I think I can do that, guys. Let's not bite off any more than that for now. We need some confidence here. Right, A. Today, we're going to do A. So we've got f of x equals that funny beast. Well, I think that's a product rule, don't you? I can see a product rule there. And that's u, and this one is v. So let's do, we won't be an algebra hero, we'll just do du dx and v dx, and then we'll do them separately, okay? And then we're going to put them together in the product rule thingy. There's du dx, there's dv dx. Oh, the dv dx is nice and easy, isn't it? Okay, here we go. Let's put them together. F dash x equals u dv dx plus v du dx, which I affectionately call left d right plus right d left. Much nicer and easier to remember than that funny thing. Now, okay, there's left d right, and following it is right d left. Now I can see some cleaning up happening there. I can see a common factor of x minus a, so let's do that. Good. Now I think I need to simplify what's in that square bracket. Yes, that's pretty interesting, isn't it? I think that's probably it, isn't it? That's f dash x. Oh, hello, Mr. Box. Thank you so much. Thank you for doing that for me. Now, alright, so take a deep breath. Have you got your chill pill ready? Good. Let's go for B. Find the coordinates of the stationary points. Oh yeah, that's easy. Stationary points mean dy dx equals 0, don't they? So let's do that. So if f of dash x equals 0, we've got that thing equals 0. Now the null factor law is going to kick in for us. Either that equals 0 or that equals 0. So let's solve it now for x. X is a, or x is that thing. Okay, well that's alright, isn't it? But they asked for, now go back and read the question, the coordinates of the stationary points. Did you see that? Don't go leaving it like that. That's not the answer. Okay, Mr. Snail, thank you. Good, now what do we got? Oh, yes, if x equals a, we're just plugging a into the boxed equation there, and what are we getting? Oh, we're getting 0. Yes, we are. Good. Now, if x equals the other one, then fasten those seatbelts, guys. Here it comes. Oh, look at all that. Goodness. Now, what did I say? I'm just plugging a plus 2b over 3 into it, right? But it's considerably nasty, so we're just going to do one line at a time, inch by inch. Anything's a cinch, and not lose our cool. Okay, I common denominated the first term, didn't I, right? And I common denominated the second term. Well, that's easy enough. Now let's simplify. What did I do there? I'm trying to work it out. Oh, okay. Yeah, I did two steps at once. I did a minus 3a is minus 2a in that first term, and therefore minus 2a plus 2b. I took the 2 out, and then I've just left what's in there. Okay, that's all right. Don't freak out. That's all right. So we've got that, haven't we? And I've simplified the second term because 2b minus 3b is just minus b. Okay, that's good, isn't it? Now let's. Oh, gee, I've just noticed something. Do you see that minus a plus b in the bracket in the first term? If you square that, it's the same as a minus b all squared, isn't it? Because the minus, if you take the minus out, call it minus a minus b, then the minus times a minus, when you're squaring it becomes a plus. If you know what I mean, I'll show you. I'll show you. That's what it is. Now you check that out. It's true. It is true. Okay? The reason I wanted to do that is because I could see that then a minus b would be common to the first bracket and the second bracket, which means I can simplify it greatly, and I get this little beast. Very excellent. Now I think that is my y value for the second stationary point, right? So I've got to state an answer now. Stationary points are that horrible one, and the other one, which was nice and easy. And Mr. Box has kicked in without me even asking him. Thank you, Mr. Box. Okay, we've done it, and I did it without the calculator. Now you can do the same thing if you just chunk it down and take inch by inch. Anything's a cinch, yes? Okay, we did it, didn't we? So that's A and B done. Done. Now let's go for C. Now this part is the absolutely insane one, and we are going to chunk it down and own it. Show that the stationary point at A is always a local maximum. Well, I mean, really, how are we supposed to show that? We haven't even got any numbers. We've just got A's and B's. Fear not, fear not. We'll see. It's easy, actually. Yes, a big few for that stuff. That was pretty nasty, wasn't it? But we did it anyway. Yes, you can. Over the page. Right, here we go. Now, we've got to show that the stationary point at A and 0 is a local maximum. Now, you might want to pause the video at this point and see whether you can do that. Because, let me ask you a question. How do you always show in methods that something is a local maximum or a minimum? How do you do that when you haven't got A's and B's, you've got numbers? You do what's called a gradient table. Now there's my hint. Now if you want to pause me now and see whether you can do it. Okay, well here we go. I'm going to show you how I did it. Okay, I had to think about it too, by the way. I had to think about it a lot. So, it doesn't come like falling off a log, but it's great for your brain and your confidence when you get these done. Alright, here we go. Now, yes, that's right. That's how you probably feel, but in a moment you're going to feel like this. Yes, you are. Alright, so here's the graph. Now, this is what I'm going to just show you. That's what we're trying to do, show that this thing's a local maximum, always when x is a. So we've got to sample the gradient just to the left of a, at a, and just to the right of a. And if we get a positive, 0, negative gradient respectively, before, at, and after a, greater than a, then we've proved it. It's all we've got to do, okay? Yes, that's what we're supposed to do. Now, yes, positive there, 0 there, and negative there. If we do that, we have proved that A always has a local maximum. And believe you me, it's easier than you might think to prove. Now, let's just write down the expression of f dashed of x. It's equal to that beast. Now, you'll see I've simplified what's in the second bracket a little bit. I've put a minus out the front, and I've bracketed the a and the 2b together. Okay, there's a method in my madness, okay, after I thought about this for a while. Now, the deal here is, guys, we're going to analyse what each of those brackets are. So I'm going to call that one A, and I'm going to call that one B. I'm going to analyse the sign, the SIGN sign of them, at each of those 3 points. And you wait to see how marvellous the result comes out. Okay, the sign of A. Now, alright, if x is less than A, then that's not rocket science. If x is less than A, then x minus A has to be negative, doesn't it? Yes, it does. If x is greater than A, then A has to be positive. Good show. Well, we've analysed that first bracket very easily. So, now we've got to do B. Now, B is a little bit more nasty, but hey, it's not that difficult. So, Mr. Second bracket, here we go. We're going to work you over. Now, I've just drawn you another little diagram there because I want to show you what we're doing here. We have to sample at those 3 points. Now, that third point that I'm sampling, by the way, it has to be greater than A, but still less than A plus 2B over 3. Do you get that? That's what you have to do. Now, what have I said there? I'm going to take the two cases for that second bracket B, purple bracket B, if you know what I mean. Now, first of all, when x is less than A, I'm going to show you what it's going to be. Okay, when x is less than A, we know that 3x must be less than 3A, mustn't it? Of course it must. So I'm working up to what's in that second bracket, that B bracket, okay? Now, therefore, 3A, because A is less than B, they told us that in the start of the question. Therefore, if A is less than B, you think about that. If you've got an A plus 2 B's, each of those 2 B's is more than an A in themselves, therefore A plus 2B has to be bigger than 3 lots of A, doesn't it? It certainly does. So therefore, if you don't get that, pause me and think about that, because it's perfectly true, okay? Therefore, if 3A is less than A plus 2B, therefore 3x already being less than 3A must also be less than A plus 2B, and therefore the 3x minus something that's bigger than it must be less than 0. Okay? So therefore, we've just proved, ladies and gentlemen, that when x is less than A, that second bracket B must be negative. Now I'm going to do when x is in that second region, bigger than A but less than the second stationary point. Okay? Same sort of argument. If x is less than that thing, that second stationary point, now think about this, therefore 3x must be, I've just multiplied both sides by 3, a typical inequation. Therefore 3x must be less than all that, and therefore 3x minus it must be less than 0. Voila! It's that easy. Okay, so therefore, when x is greater than A but less than the second stationary point A plus 2B over 3, then 3x minus that thing, which is the B bracket, must be negative. Oh wow! Now it's getting to an exciting climax now. I'm going to do a table for you and show you what's going on. Now, okay, let's do when x is certain, when we'll test x at each of those 3 points, okay? Then we're going to do the sign of A, the sign of B, and then the sign of their product, okay? Gee, this is great. When x is less than A, we know that. We've just found out, guys, that the first one, the sign of A, if you look back to the lower left-hand side of this screen, you'll see it was negative. What about the sign of B? Look at the upper right-hand side of the screen, and you'll see that that was also negative. So therefore the product of a negative and a negative is positive. Now let's do the next bit. What about when x is between the two stationary points? Well, we also found out that when x was greater than A, lower left-hand side of the screen, we got positive for bracket A. And for bracket B, we still got negative. So therefore the product is negative. So now, finally, when x is at A, well, it really doesn't matter because the first term is 0. We don't care what the second term is, and therefore the result is 0. So now let's tick them off, guys. Let's tick them off. When, a little blue tick, lower right-hand side, I'm saying that when x is less than A, the product is positive. So look at the little graph I've got up in the middle of the screen. That means, yes, we've got a positive there. Okay, now, bottom right again, we've got when x is between the stationary points, the product is negative, and I'm putting a blue tick on the screen, in the middle of the screen on the graph. You can see it. I've proved it's negative, and I've also proved that when x is A, the thing's 0. How sweet it is. I've just proved it. I've just proved it. So therefore, we can say with a surety that the stationary point at A and 0 is always a local maximum, and triumphantly Mr. Box is going to help us put the icing on the cake. Thank you, Mr. Box. Now come on, you guys, that wasn't that difficult. It might look impossible, but if you just have confidence in yourself and get a bit of positive psychology and believe in yourself, you can do that. Come on, I'm no genius. and I did it, so you can do it too. So just have a go. You never know what you can do. Now, there's the end of my pep talk. I think we have to do D yet, don't we? All right. Oh, yes, yes, Mr. Thumbs Up. Yes, it's so wonderful. Okay, over the screen, number D. We're all excited, but we've done it really. This bit's the anticlimax. Find the values of A and B if the stationary points occur at 3 and 4. Oh, no problem. I can smell some simultaneous equations here. Stationary points were X is A and X is that thing. Okay, now you know that B is greater than A, so therefore A has to be 3, doesn't it? Of course it does. A has to be 3. So therefore we just plug that into the second one, and call it 4. And it's all over by the shouting. And we just solve it for B, for you and me, which fills us with glee, and we say yippee, and we get B is 9 over 2, and then we can do some boxing again, I think. Yeah. Yes, yes. So what's the theme of today, guys? What is it? Yes, that's what it is. Yes, that's what it is. So, well done. And we'll go forward and onward, ever onward. That's the end of that question. We demolished it, didn't we? Alright, what's the next one? Graph of the function y equals x cubed minus 3x squared is translated by A units in the positive direction of the x-axis and B units in the positive direction of the y-axis, and A and B are positive constants. Well, I can't see any A's or B. Oh, yes, I can. I see. We translated it by A to the right and B up. So is that all we have to do? Find the coordinates of the turning point. Oh, first of all, of that one, there's no A's and B's in that, so we can easily do that, guys. Let's do that, and we won't even think about B yet. So y is that thing. So what's dy dx? It's that thing. So if we set it to 0 at the turning point or the stationary point or whatever you want to call it, we get that, and we solve it for x. Take out the common factor. Null factor law tells us that. No problem. Now what are we doing? We're finding the coordinates. Look at the question again, don't leave it. Okay, so we've got to find the y values now and put them in brackets as x comma y's. So yeah, righto, so if x is 0, well, that's pretty obvious. Y is going to be 0, isn't it? Yeah, yes, 0. So what about if x is the other one? If x is 2, y is that, all that. Now what's that come to? Comes to that. And that comes to that. So now we'll put our answer in proper form so we can't lose our marks. And we're going to put a box around it. Beautiful. There it is, guys. Yeah, there it is. Now, what are we got to do now? B, for you and me. Find the coordinates of the turning point of the image. That's after we've done the translation on it. Well, what is it doing? It's going over x over by A and y up by B. Well, that's pretty easy, isn't it? Goodness. We've just got to... so therefore, if we go A units over to the right, B units up, then what happens? Yeah, 0, 0 becomes A and B, doesn't it? I think so. And then the other one does the same thing. You just add A to the 2 and B to the minus 4, and you've got it. That's all you need to do, because we're only translating points here. We're not trying to come up with a new function, guys. If we were coming up with a new function, then you have to apply your rules, okay? But we're just translating points here. Maybe that's the trick in this question. It's not very tricky, is it? Mr. Box, okay? Excellento. Now, I think I've got another yes you can. That's right. Yes you can. Yes you can. And well done to you for doing such a good job. Righto. I think we're going to go over the page. Goodness. Matrices. Oh, time to hit the panic stations. Take the chill pill. No. We can do this. A cubic function has the rule of that thing. Well, that's not too scary so far. It passes through the point 1 and 6 and 10 and 8 and has turning points that. Well, I've got 4 clues there, guys. Did you spot them? 1 and 6 is clue 1, 10 and 8 is clue 2, and the turning points are clues 3 and 4. Therefore, if we've got 4 pronumerals to sort out, if that's what they're asking us to do, yes it is. In A, we can do that, no problem. But we have to use matrix methods. Okay, look, I'll show you how to do that. It's a piece of cake. A. Yeah, 4 pronumerals to find, 4 clues, which is equations, and we just have to go through the motions and just get it. Get it, guys. There it is. Now let's put our equations in. We'll do 1 and 6 first, shall we? Yep, and sub that. So we get that thing, that's equation 1. Now what's our second clue? 10 and 8. That's going to be a bit nasty because I've got cubing, and with x is the 10. Goodness, I'm going to get some enormous thing out of that. Watch. We sub that in, and we get this. Ooh. Never mind. That's all right. We can cope. We're using matrix methods. We don't have to do it by hand. Thank goodness. All right, clue 3. Now, for clue 3, we have to take the derivative because these are about stationary points or turning points. So dy dx is that beast. Now we're going to plug in x is minus 1 and dy dx is 0. And what do we get? We get that. Now we're going to sub in x is 2 and dy dx is 0. What do we get out of that? No problem. Now we've got 4 equations, guys. Now, look, I'm going to rewrite them all out again so that I'll know how to construct a matrix out of this thing. You're using matrix methods, Mr. Snail, thanks. Now, there's number 1. Here comes number 2. And here comes number 3, and here comes number 4. Now, here's my question to you. Do you know how to turn that into a matrix equation? Well, if you don't, you better go back and revise your matrices because it's very, very easy once you know how. Here it comes. Ooh. Good heavens. So if you read that off, the coefficients of each of those terms in the 4 equations are in what is the first matrix, okay? A, that's 1A plus 1B plus 1C plus 1D. Gets you the 1s in the row, or the first row of the first matrix, and so on and so on. And then the A, B, C, D go in the column of the second matrix, right? And the right-hand side goes on the right-hand side of that right-hand side matrix. And that's what and if you read that off in a matrixy way, that's what you will get. Exactly those 4 equations above. Okay? Right? I'll just do the second line for you. So 1000 A plus 100 B plus a 10 C plus 1 D equals 8. Right? You're doing the first item of the row multiplied by the first item of the first row in the second matrix, and so on and so on and so on. Do you know what I mean? Yeah, alright. Now, what we have to do is we have to turn that into a matrixy equation, so I'm going to define them as follows. Okay, AX now, look, that looks weird, but capital A is the first matrix, capital X is the second matrix, and capital B is the third matrix. Now, we have to solve it for capital X, which is A and B and C and D. Now, in order to do that, you multiply the left-hand side and the right-hand side by the inverse of capital A. And if you do that, the A to the minus 1 times the A gets you magically disintegrates into the identity matrix, which is just 1. And you get this. Yeah, so that's what I'm going to do. Now, I think I'm going to go over the page and do this for you on the calculator. Okay, ready, set, go. Now there's my calculator calculation. See now, do you see there I've defined that big beast as matrix little a, because I can't be bothered doing capital A's on the calculator, and I stored it in, okay? That's the first tick. Now, then I defined the second right-hand side over the other right-hand side of the equal sign on the previous screen, in that AX plus B thing as little b. Okay, little b, and there it is for you and me. And then I did the old knockout punch. I said A, the inverse of A times B, and look what I got. Look what I got. There they are. There's capital A, or there's little a, there's little b, there's little c, there's little d. Now, no wonder they asked us to do that with matrix methods. My goodness. Imagine doing that by hand. Chill pill just wouldn't do it, would it? Okay, well, we've done it. We did it. Are you pleased? I'm delighted. Now, we haven't finished with it yet. We've done A. We've done part A. Now, what are we going to do now? Alright, we've got to do part B, which says find the equation of the image of the curve under the transformation defined by the matrix equation, blah, blah, blah. Oh. Well, look, guys, that thing that you're looking at is the key. I call it the matrix key. And it is the key to unlock the door of all the mystery and intrigue that is staring us in the face with that beastly looking matrix equation. However, it's not hard at all, actually. You see the equation above, the cubic equation above, y equals ax cubed plus bx squared plus cx plus d. Well, all we've got to do is plug the key, which we're looking at there, into that, because the image comes from that key. But you see, the matrix, the equation above has x's in it, right? X's and y's in it. And the equivalent of that beastly looking matrix equation is the x's and the y's, the little x's and little y's reside in the big X term. Okay? And the x dashes and the y dashes, the transformed ones, they reside in the x dash term, the capital X dash term. So we have to solve that thing, that beastly matrix thing, by solving it for capital X. And then once we get that, we've made little x, little y the subject, because they're inside capital X, if you know what I mean. And then we can just plug them straight in, plug the key straight into the equation, and we get our image. That is my game plan. So don't be put off by these matrix things. They're just wolves in sheep's clothing. Okay? Oh no, what are they? Well, the other way around, I think. They're not harmless. Okay, their bark's worse than their bite. Right, B. Here we go. Now, okay, I got that. Now what I'm going to do is I'm going to get my matrix equation and I'm going to solve it for capital X. That's the objective. So how do I do that? Yeah, first of all, I'm going to get rid of that t out the front by multiplying it by its inverse, left-hand and right-hand side. That dissolves the t thing and gives me that. Good. Now, I think I probably need to work out what inverse of t is now. T's that thing above, that 2 by 2 matrix above. So, yeah, and of course, capital X would be t, that thing, subtracting b from both sides, yeah? So now I've done it. So that's all I've got to get to, guys, and I'm there, okay? So if t is that thing, I'm going to find its inverse. Now, if you don't know how to find the inverse of a matrix, you better go back and figure it out. But you have to go 1 over the determinant, which happens to be 1 over 6 is the determinant, and then you have to reverse, you have to negative those terms which are zeros, and they're already 0 anyway, and you have to, no you don't, you reverse them. You reverse the zeros, but they're already zeros, and then you negative those other terms. The minus 3 and the 2 become plus 3 and minus 2, if you know what I mean. Okay, that's the inverse of t. Now I think we're pretty right to go now. We can work out, yeah, I just simplified it a bit. I put the sixth outside, inside. Now, what am I going to do now? Yeah, therefore capital X is that thing, and let's go for it now. Now I'm putting it into more friendly terms. See, I'm putting what capital X is and what capital X dashed is, because that's what we're after, okay? Now I'm going to work them out now. It's easy to work them out using matrix techniques. That's what they come to, and that is my key. That's my key for you and me. I'm just going to put that X into the original equation and that Y into the original equation. I've got my image. The key makes it easy for you and me. Yeah, into there. Here we go. I'm nearly there, I'm nearly there. Now that looks like an absolute beast, and it is. But we don't have to do any more with it. That's all we have to do. What I would probably write on the answer there is that A, B, C and D, pronumerals, are the values that we got in part A. And we don't have to repeat them because they're too ridiculous. So that's it, Mr. Box. Thank you so much, Mr. Box. Alright, now that's a bit of quick revision in matrixy stuff, okay? And we did it, didn't we? We did it. So come on. Yes, we sure did. All right, another one. I think this one's really easy. Alright, let's go for it. We've got a cubic equation. This time there's no d term on the end, it's just ax cubed plus bx squared plus cx. We know that it has a stationary point at 1 and 6. Well, I can see two clues there, guys. I can see that it goes through 1 and 6, and it has a stationary point at 1 and 6. So I can see two equations popping out of that. But but there's A, B, and C. So obviously we can't solve it for everything. We need 3 equations for 3 pronumerals. So that's why they're saying they want us to find A and B in terms of C, because we can't resolve all 3 of them. Okay? So let's do that. There are 2 clues, 2 equations. Okay, let's go through it. Sub 1 and 6 in, and we can see that 6 equals A plus B plus C. By the way, please make your 6's different from your B's, because you've got no idea what happens to some students' work because a B morphs into a 6 or vice versa, and their answers go haywire. So mine's a little bit dodgy there. That's what reminded me to tell you. So I have to be careful. Therefore, f dash of x is that thing. Yes, yes. And we're going to plug in the stationary point now. Okay, and we're going to get our second clue. There it is. Now I've got 2 equations, guys, and I've got to find A and B in terms of C. Now I'm not going to use the calculator. I'm just going to do it the slow way, but it's great for my confidence. Solving simultaneously, so I'm getting A in terms of B and C from equation 1, and then I'm going to sub that into equation 2 to get B in terms of C. And here it comes. Da-da-da-da, and it's just simplifying. Be careful, don't lose your cool, we're nearly there. Yes, and therefore B is that thing. It's just beautiful, isn't it? Now we're going to sub for B into equation 1, because 1's probably the easier one to sub into, and we're going to get A in terms of C doing that. Yes, yes, yes. And where are we? Yeah, we've got that now. Box time. Hey, beautiful, isn't it? So that's it. Now we've got to do question B. So what have we got to do there? We've got to find the value of C for which the graph has a stationary point when x is 2. What? Find the value of C for which the graph has a stationary point at x is 2. I think I can do that. I've got the derivative, haven't I? The derivative is 3ax squared plus 2bx plus c, but I know a and b in terms of c, don't I? So really I only don't know, sorry for the English, c. And I think that enables me, that third clue enables me to solve it for c. So yeah, that's it. That's exactly what I thought, Mr. Computer, thank you. So f-x is all that. I'm going to substitute for c, because I'm going to use all that work that I just did in part A of the question. And I'm now going to substitute when x is 2, and then c becomes